Okay, now in section 1.6, we determine and discuss inverse functions and logarithms. Now, we have a definition here, and the definition states that a function f is called a one-to-one function if it never takes on the same value twice. And that is, if the output of x1 does not equal the output of x2 whenever x1 does not equal x2. Now, if a function is an inverse function, it has to be a one-to-one function if it has an inverse. So if you take a look at the mapping over here, okay, the first mapping here is the function for f. So that means you have an input that goes to one output, or in this case, one output has one input, one output has one input, one output has one input, and so forth. Therefore, this is a one-to-one function. Now, if you look at this mapping, which is function g, this is not a function because the output of 2 goes to one input, which works, but then the output of 4 goes to 2 inputs. So again, in the language of inputs and outputs, this definition says that f is one-to-one if each output corresponds to only one input. Now, another scenario here is if we're looking at a graph. Now, if you look at the figure 2, we have a function that's in blue. And if a horizontal line intersects the graph of f in more than one point, then we can see from figure 2 that there are numbers x1 and x2 on this graph, such that the outputs of x1 and x2 are equal to each other, because it has the same distance. This means that f is not a one-to-one function. Therefore, we would have the following geometric method for determining whether a function is one-to-one. So in this case here, that means that this function does not have an inverse. Now the horizontal line test, what it does is, it tells us that a function is one-to-one if and only if no horizontal line intersects its graph more than once. In this scenario, it intersected twice. Okay, let's take a look at the first example. We want to determine if the function x cubed is a one-to-one function. So there's two ways of determining this solution. Okay, the first one is basically stating, okay, well, we know that from that definition, if x1 does not equal x2, okay, then we can say that because this is a cubic function, then we can say that x1 cube does not equal x cubed 2. Okay, so the two different numbers can't have the same cube. So by definition, we could say that the function f of x, which is equal to x cubed, is 1-to-1. Okay, now from solution number 2, okay, from the figure, meaning that if we graph this function, we can see that there's no horizontal line that intersects the graph of x cubed more than 1. So therefore, I'm going to abbreviate this, that the horizontal line test would then tell us that it is what? A one-to-one function. Now, let's take a look at the next example, where the function g of x is equal to x squared, and we want to know if this is one-to-one. Now, again, if we take a look at the first step, okay, we want to determine if this function is a one-to-one function. But it's not one-to-one function, because it's saying here that if you take the input, okay, g of 1, so the input is 1, correct? And then the input of -1 also has an output of 1. So because you have one output that has two inputs, then it's not 1-to-1. which means it does not have an inverse. Okay, now in 2, okay, again, does this pass the horizontal line test? Well, it doesn't, because it passes through the function more than once when you're using the horizontal line test. So therefore, by the horizontal line test, we could also say that this is not a one-to-one function. Now, one-to-one functions are important because they are precisely the functions that possess inverse functions. And so according to the next definition. So the definition, we let f be a one-to-one function with domain A and range B. Then its inverse, f inverse, has domain B and range A and is defined by the following. So f inverse of y is equal to x. And what happens is now, since the f inverse, y is the input, x is the output, whereas f of x, x is the input, and that's equal to y. So basically what happens is the domain and range have also an inverse. Now this definition says that if f maps x into y, then f inverse maps y back into x. That means that if f were not one-to-one, then f inverse would not be uniquely defined. So the arrow diagram that you're going to see right here, okay, indicates that f inverse reverses the effect of f. So f inverse reverses the effect of f. And note that the domain of f inverse is the range of the original function, and the range of f inverse is equal to the domain of the function. So let's take a look at an example algebraically here. Okay, so let's say that we have the function f of x, which is equal to x cubed. And its inverse and we would say this is f inverse of x, would equal the cube root of x, or x to the 1/3. And that's because f of x, or y, is equal to x cubed. So if we use our definition from above, we would say that f inverse of y, okay, and what does y equal here? Well, it equals x cubed. So we're going to substitute the input y to be x cubed. So now the input is x cubed, okay? And now what we're going to do is we're going to put this input into the inverse. So now we're using the idea of composition. So now we're going to substitute the x up here to be x cubed, and that's going to be raised to the 1/3 power. And so ultimately, when we raise x cubed to the 1/3, well, 3 over 3 becomes 1, and so you're left with the value of x. So that determines that they are inverses of each other. Now, we also want to make sure that we take a little bit of caution here. Do not mistake the -1 in f of -1 for an exponent, because f inverse of x does not mean 1 over f of x. Now, the reciprocal 1 over f of x could, however, be written as f of x is -1, but be careful of that notation. Okay, let's take a look at example number 3. We want to be able to evaluate an inverse. So if f of 1 is equal to 5, and f of 3 is equal to 7, and f of 8 is equal to -10, okay, we want to be able to find f inverse of 7. So f inverse of 7 would equal 3. And that's because the given information told us that the input was 3 and the output was 7. Similarly, if we want to find f inverse of 5 being the input, well, again, take a look at what's given. Well, when 5 is the output here, then that means that the output for the inverse would then be 1. And again, that's because from the given information, f of 1 is equal to 5. And if we want to find f inverse of 10 when 10 is the input, well, what is the output? Sorry, not 10, but negative 10. Then the output is 8. And that's because when the input is 8 of that function, the output is negative 10. Okay, so let's take a look at the mapping here in the reversing effect of f. So this is another way of looking at this. You have a map. 1 is the input, for 5 is the output, 3 is the input, 7 is the output, 8 is the input, negative 10 is the output. That is f. Now f inverse now maps b to a. So 5 is the input, 1 is the output, and so forth. So that basically just tells us that it's an inverse. Now, if the letter x is traditionally used as an independent variable, so when we concentrate on f inverse rather than on f, we usually reverse the roles of x and y in definition 2 and write the following. So f inverse of x is equal to y, which means f of y is equal to x. Now, by substituting for y in definition 2 and substituting for x in 3, we get the following cancellation equations. When f of x is the input for the f inverse, it's equal to x for every x in a. And when f inverse of x is the input of the function f, that's equal to x for every x in b. Now, the first cancellation equation says that if we start with x, apply f, and then apply f inverse by using the composition, we arrive back at x, where we started. So see the machine diagram in this figure 7. Thus, f inverse undoes what f does. So the second equation says that f undoes what f inverse does. So again, let's take a look at example. So if we said that f of x is equal to x cubed, then we stated earlier that f inverse of x is equal to x to the 1/3. And so if we apply those definitions, meaning that if we have f inverse and the input is f of x, so what does that equal? Well, that means that the input is x cubed for the function f inverse. So we saw that where you have x cubed raised to the 1/3 power, and that would give us the value of x. Okay, and then when we have f and the input is f inverse of x, And you can see here that the input then would be x to the 1/3, and we would have to cube that function. And when we raise it to the 3rd power, we also get x. So this is the idea of the cancellation. So these equations simply say that the cube function and the cube root function cancel each other when applied in succession. All right. Okay, now here is definition 5. How do we find the inverse function of a one-to-one function f? Well, the first step is to write y is equal to f of x, then solve this equation for x in terms of y if possible, and then step 3, express f inverse as a function of x, interchange in x and y, and the resulting equation would then be the inverse. So let's take a look at example number 4, where we want to be able to find the inverse of this function. So again, the first step of what we want to do is replace f of x to be y. So y is going to equal x cubed plus 2. Now, the second step is to interchange x and y. So we're going to replace y to be x, and x is going to be y. So we have x, which is equal to y cubed plus 2. And now the goal here is to then solve for y. So if we solve for y, we should get y cubed, which is equal to x minus 2. And now if we want to solve for y, we would have to take the cube root of both sides. So we would have the cube root of x minus 2. And so we are almost finished, because now we're going to replace y to be f inverse. So now f inverse of x would then be the cube root of x minus 2. Okay, now the principle of interchanging x and y to find the inverse also gives us a method for obtaining the graph of f inverse from the graph of f. Now, since f of a, meaning a is the input, equal to b, if and only if f inverse of b is equal to a, then the point AB is on the graph. If f of f, if and only if the point BA is on the graph of the inverse. But we get the point BA from AB by reflecting about the line y equals x. So the line here in green represents y equals x. And you can see here that you're reflecting. So if this is the line here and this is a line here, and it has a point AB, okay, you can see that this line forms a perpendicular here. And if you invert these 2 points, you would have this line here, which is BA, and again, here is your perpendicular. So again, the line y equals x is the line of symmetry for this inverse. And the same thing here for figure number 9. So therefore, we can say that the graph f inverse is obtained by reflecting the graph of f about the line where y is equal to x. Okay, now in example number 5, we're sketching a function and its inverse. So we sketch the graphs of f of x is equal to the square root of -1 minus x and its inverse function using the same coordinate axis. Okay, so let's go ahead and find the inverse of this function. Okay, so step 1, again, we're writing here, we're going to replace f of x to be y. So we have y, which is equal to the square root of negative 1 minus x. And then step 2, we're going to replace x with y. And then in step number 3, we're going to solve for y. So we'll rewrite this where we have the square root of negative 1 minus y, which is equal to x. So in order to get rid of the square root, we're going to square both sides. So we have negative 1 minus y, which is equal to x squared. And then negative y, which is going to equal x squared minus 1. And then ultimately, we would say that y is going to equal negative x squared minus 1. So the inverse of that function is equal to negative x squared minus 1. So here we're going to graph these two functions, and let's see what it looks like on the graphing calculator. So we'll go ahead and put that on a graphing calculator here. Let's go ahead and clear all that out. Okay, so our function here, we have second square root of negative 1 minus x. And then we have the line y is equal to x, since that's our line of symmetry. And then we have negative x squared minus 1. We'll go ahead and graph that. Okay, so when we graph that, our window doesn't show, so we need to at least bring our windows a little bit closer. So we'll go ahead and do that. So we'll have negative 5 and then 5 for our x values, negative 5 for y, and 5 for y. And so now you can see that this looks like the graph that we have here. Now, if you notice, you see this graph here? We need to look at its domain, or in this case, range, right? So what's going on with the domain and range? Well, we have to cut this part of the graph off because this graph right here would not be a one-to-one function. So you can see here that this represents the inverse of that function depending upon its domain. So if you look here, what is the domain of this function? This is really important. So the domain of this function, okay, means that we have negative 1 minus x has to be greater than 0, greater than or equal to 0. So we have negative 1 or negative x, which is greater than or equal to 1. If we divide both sides by negative 1, then that means we need to flip the inequality, so x is less than or equal to negative 1. So if you look, that tells us what the domain is here. Okay, so if that is the domain of the first function, then recall that that has to be the range of the inverse. So if you look here from negative 1 down, that is the range. Now, the range of the original function starts where? It starts at 0 and it goes to positive infinity. So then what would the domain then be for this? Well, we know that the domain would have to be the range. And you can see here it starts at the value of x and goes to positive infinity. So that's another important element of inverse functions. Okay, then we have logarithmic functions. So if a is greater than 0 and a does not equal 0, the exponential function f of x is equal to a to the x is either increasing or decreasing, and so it is a one-to-one function by the horizontal line test. It therefore has an inverse function, which is called a logarithmic function with base a, and it's denoted by the log of base a. If we use the formulation of an inverse function given by that theorem 3, so f inverse of x equals y, where f of y is equal to x. Same thing here. The log of base a is equal to x is equal to y. So the best way to look at this is saying that y is the exponent on base a to get x. And then we would rewrite that as an exponential form. So again, y is the exponent on base a to get x. Now, the log of base a to the x, is equal to x for every x value that's all real numbers. And the base a that has an exponent of log of base a x is equal to x for every x being greater than 0. Now, let's take a look at these two figures. This first figure is figure 11. It shows the case where a, meaning the base, is greater than 1. So the most important logarithmic functions have a base of a greater than 1. The fact that y equals a to the x is a very rapidly increasing function for when x is greater than 0. And it's reflected in the fact that the logarithmic function, which is the inverse, is a very slow increasing function for when x is greater than 0. And again, that's because they are inverses of each other, with the line of symmetry being y is equal to x. Now, if you take a look at figure 12, okay, it shows the graphs of the log of base ax with various values of the base a being greater than 1. So since the log of base a1 is equal to 0, the graphs of all logarithmic functions pass through the point 1, 0. So you can see this one is slow compared to the one with the base of 5. And as the bases, you can see here, decrease, then it rises a lot faster than the previous ones. Okay, then we also have the laws of logarithms. So if x and y are positive numbers, then the log of a, xy, would then expand to the log of base a plus the log of base ay. The log of base a x divided by y would expand to the log of a of x minus the log of ay. And then the log of base a, this is the power rule, x to the r. You would then replace r as a multiplication of the entire function of the log of base ax, where r can be any real number. Now, using these laws, we're going to go ahead and evaluate the following. So we have the log of base 2, 80, minus the log of base 2, 5. Now, they do have the same base, but we can't evaluate 80 and 5 in terms of having a base of 2. So we have to use some of our properties. So the property we can see is, since this is subtraction, this would turn into division. So now we're going to have the log of base 2 of 80 divided by 5. And what is 80 divided by 5? Well, 80 divided by 5 is 16. And so now how can we get a base of 2 with 16? Well, the log of base 2 is the same thing as 2 to the what power? To the 4th power. So then we would ask ourselves, okay, now what is the exponent on base 2 to get 2 to the 4th power? Well, then the answer would then be 4. Okay, now of all the possible bases for logarithms, we will see that when we get to chapter 3 that the most convenient choice of a base is the number e, which is defined in section 1.5. The logarithm with the base e is called the natural logarithm and has a special notation. The log of base e x is also equal to the natural log of x. If we put a equal to e and replace log of base e with a natural log, as in theorems 6 and 7, then the defining properties of the natural logarithm function become the following. So it's basically the same, but just we have natural log of x is equal to y, and the exponential form is e to the y, which is equal to x. The natural log of e to the x is equal to x when x is any real number, and e to the natural log of x is equal to x when x is greater than 0. In particular, if we set x is equal to 1, the natural log of e is equal to 1. Now, in calculus and science, as well as calculators, we use the notation the natural log of x for the natural logarithm and log of x for the common logarithm. So in more advanced mathematics and scientific literature and in computer languages, however, the notation log of x usually denotes the natural logarithm. So let's take a look at example number 7 here. We want to be able to find x if x is equal to 5. So again, using theorem 8, we would say that the natural log of x is equal to 5. So what is the base of the natural log? Well, we know that it's e. So now what we want to do is we want to convert this into exponential form. So by converting it into exponential form, we would say that 5 is the exponent on base e to get x. So therefore, what does x equal? Well, it equals e to the 5th power. That's one way of finding the solution. Now, another way, we can start with the equation the natural log of x is equal to 5. And now applying the exponential function to both sides of the equation, meaning that if we apply e to the natural log of x, and then applying it on this side, e to the 5th power, well, what do we know about e to the natural log of x? Well, according to the definition in part 9, this becomes x, which is equal to e to the 5th. So again, there's various ways of being able to solve your natural logarithmic equations. Now let's take a look at example number 8. We want to solve the equation e to the exponent 5 minus 3x is equal to 10. So looking at this equation, we can see that x is located in the exponent. So because it's located in the exponent, then we want to be able to use the idea of logarithms so that we can solve for it. So what we can do on both sides here is take the natural log of both sides. And then what that allows us to do is that'll allow us to then use the properties of logarithms. So since this has a base of e, then we can say that the natural log then just of e to the 5 minus 3x becomes 5 minus 3x, which is equal to the natural log of 10. And now it just becomes an equation, and we're solving this equation. So we have negative 3x, which is equal to the natural log of 10 minus 5. And so divide both sides by the negative. We have 3x, which is equal to the negative natural log of 10 plus 5. And therefore, x would then equal the negative natural log of 10 plus 5 divided by 3. All right, now we could also approximate this particular answer from the previous example. So if we wanted to plug this in our calculator, then we can approximate this result to 4 decimal places, which would be 0.8991. Okay, now using the laws of logarithms, so we want to express the natural log of a plus 1/2 the natural log of b. So we want to take this expression, which is expanded, and condense it into one single logarithm using our properties of logarithms. So the first thing we want to do is apply the power rule by rewriting the 1/2 as an exponent of b. So this becomes a natural log of b to the 1/2. And recall that this is a fractional exponent, which can be written as a root. So therefore, this is the natural log of the square root of b. And now we can rewrite this using the property of addition with logarithms, and that becomes multiplication. So this becomes the natural log of a times the square root of b. Okay, now we also need to use the change of base formula. So for any positive number of a, where a does not equal 1, we have the definition that log of a of x is equal to the natural log of x over the natural log of a. Okay, so in order to apply that rule, let's evaluate the log of a of base a to the 5th, correct to 6 decimal places. So using that formula, we know that a represents 8 and x represents 5. So the log of base a of 5 is equal to the natural log of 5 divided by the natural log of 8. Now the reason why this formula exists is because you don't have a base of 8 in your calculator. So if you use the change of base formula, then you're able to come up with an approximation or an exact answer. And again, since we're finding it to 6 decimal places, this would be approximately 0.773976. Now we want to be able to interpret an inverse function. In example 3 in section 1.5, we showed that the mass of strontium 90 that remains from the 24 milligram sample after t years was given and defined by that function 24 times t2 to the negative t over 25. We want to be able to find the inverse of this function and then interpret it. Okay, so in order to solve this equation, we first need to start by isolating the exponential and then taking the logarithms of both sides. So starting with this function m, which is equal to 24 times 2 to the negative t over 25. Okay, so we want to isolate again the exponential, so we have to divide both sides by 24. So we have m over 24, and that's equal to 2 to the negative t over 25. Okay, so now that we've isolated that, now we can take the natural log of both sides. So we have the natural log of m over 24, which is equal to the natural log of 2 to the negative t over 25. Now again, using natural logs allows us to be able to then use the power rule so that we can solve for that value of t. So now we're going to end up with, if we expand on the left-hand side, we have the natural log of m minus the natural log of 24. And using the power rule, we would have negative t over 25 times the natural log of 2. Now, if we want to solve for t, we can multiply both sides by negative 25. So we have negative 25 times the natural log of m plus 25 times the natural log of 24 and that's equal to t times the natural log of 2. So now if we solve for t and divide both sides by the natural log of 2, we can rewrite this using the positive value first. We would have 25 times the natural log of 24 minus 25 times the natural log of m over the natural log of 2. And if we wanted to simplify that a little further, we can factor out the 25 and the denominator, natural log of 2, and that would be times the natural log of 24 minus the natural log of m, and that's equal to t. So what can we determine from this? Well, we can say that t represents the inverse of m. So f inverse of m would then be 25 over the natural log of 2 times the natural log of 24 minus the natural log of m. And so what this function gives, the time required for the mass to decay to m milligrams. So in particular, the time required for the mass to be reduced to 5 milligrams would be the following. So if we wanted to find when the mass was 5 in that previous example, t would represent the inverse, where m is 5. And if we plug 5 into this function, then we would get approximately 57 or 56.58 years. Okay, now graphing growth and natural logarithm. The graphs of the exponential function y is equal to e to the x and its inverse function. The natural logarithm function are shown in figure 13 because the curve y is equal to e to the x crosses the y-axis with the slope of 1, and it follows that the reflected curve y is equal to the natural log of x crosses the x-axis with a slope of 1. So in common with all other logarithmic functions with base greater than 1, the natural logarithm is an increasing function defined on the interval 0 to infinity, and the y-axis is the vertical asymptote. So what this means is the values of the natural log of x become very large, negative, as x approaches 0. Okay, now this last example for number 12 is shifting the natural logarithmic function. We want to sketch the graph of y is equal to the natural log of x minus 2 minus 1. So again, we always graph the basic function here, which is the natural log of x, and has an x-intercept of 1, 0. And then what we're doing is we have to shift it to the right how many units? Well, from 1, we're shifting it over 2 units. So you can see where now the x-intercept is located at 3, 0. And it has a vertical asymptote at x is equal to 2. Now, if we add our next shift, which means we have to shift it down, so now at the point of 3, 0, we have to go down at 1 point. So from 0 now down to negative 1. So now we have this point now is here at 3, negative 1, and you have that vertical asymptote. Now, although the natural log is an increasing function, it grows very slowly when x is greater than 1. So in fact, the natural log of x grows more slowly than any positive power of x. So to illustrate this fact, we compare approximated values of the functions y is equal to natural log of x and y is equal x to the 1/2, which is the square root of x, in the following table. Then you can graph them. You can see that initially the graphs of y equals the square root of x and y equals the natural log of x grow at a comparable rate, but eventually the root function far surpasses the logarithm. So here you're creating this table and then comparing these two graphs. And so the reason why you're doing this is because eventually when we get to chapter 2, when we start beginning in the calculus, you'll be making tables to talk about the rate of change. So it's important to know that what happens with these graphs, being able to analyze these graphs, and what's happening when you're viewing these graphs.